Okay, so administrative stuff. This is the last class before study week, so I don't think I'm going to do any new material. I kind of thought about it. I think today's going to be the last day I cover anything new. Obviously, none of the extra topics we talked about will be on the final. That was just kind of extra stuff for fun. So next week's study week, I think we'll just do review, maybe the first day, and then if we have some time left over, if we don't finish, we'll do it the second day, and then I think I'll just let you guys go and study and not take up your time. The final exam, I couldn't find a definitive thing for this semester for whatever reason, so I'm going based off of previous semesters because I think it's about the same every semester if I remember right. So it should be, I think ours is 6 to 8. I want to give a little bit of extra time just so you have a little bit more leeway. So I'm just going to open it up an hour earlier. But if you can't make it because you're taking a different exam, you still have that extra time. And I'll leave it open 5 to 10. It should be on Tuesday of final week, which I think is the 7th. Somebody can correct me if I'm wrong. And it's going to cover all the material, so it's cumulative. It's going to cover everything from exam 1 and 2, and then stacks and queues and linked lists, which are the only things that we haven't done an exam on yet. The questions you can expect are going to be relatively similar, so it's going to take the same format. It's just going to be a bit longer. So whereas the other one was maybe an hour and a half, this one will be maybe 2 hours, 2.5 hours. I'll try to keep it short if I can. I was trying to remove some questions from it to not make it too ridiculously long. Right, so that's that. You may have noticed I put on Canvas that assignment 9 and 10 have been extended, so assignment 9 is due tomorrow night now, and then assignment 10 I pushed back about as far as I can possibly push it back and still give the TA sufficient time to grade, unfortunately for him, but so I'm not going to be pushing back assignment 10 any longer, even if people ask this time. Just consider that I still need to give the TA time to grade before grades are due, because he has finals too, right? So that's kind of set in stone. The same thing with the extra credit, which I will probably end up grading, but that's up to the same date, I think. So I think that's everything administrative wise. Did anybody have any questions on assignments 9 or 10 that you wanted to go over before we get started? Okay. I don't think I see any questions. But if you have any, feel free to stop by office hours. On that note, actually, I think I'm not going to have office hours on finals week. I think I have a meeting that week. So if you have any questions, just send me an email or Discord or come to office hours this week. And I will answer any review questions you have or assignment questions, anyways. The last assignment is due before then, so I'm sure nobody really needs the office hours that much. But yeah, I'll gonna have to cancel those. Okay, so I think that's everything administrative wise. Let's get into talking about one extra thing. This wasn't one of the topics that I had originally for the extra topics, but I thought it might be useful for everybody to have an idea of how this works. Because I think 302 teaches it now. It didn't when I took the class, but it is very useful, and sometimes compilers will do it for you. But it's good to know about, and it's very important for making your programs run fast. And that's threading is what we're going to talk about. So first things first, let's just consider, without threads or any idea of threads, let's just consider a really simple example where you're given an array and you want to find the average of the things in the array, right? So pretty easy, like CS135 level program. What we would do is we would just loop through the array, sum up all the numbers, and divide by the amount of numbers that there are, right? That's how you take an average. So you do something like a for loop for I to size. Let's write some pseudocode here. And then we'll keep some sort of sum add to it each value in the array, and then whatever we break out of this loop, we'll just take that sum and divide it by how many things are in the array. So we'll just say size. And that's how we do average, right? Pretty simple to start off with. But let's say we want to do this faster. So something to consider about, we talked a little bit about time complexity, and there's some ways to speed up things like sorting, right? And sorting has room for improvement, at least if we consider something like bubble sort, because we look at the elements more than one time. We do multiple passes through the array. But something like this, if you consider the way you have to take average, you have to look at all the numbers, you have to add them all up, and then divide by the thing. So there's no shortcuts. This is really just the fastest way you can do average on a normal computer, or like in a normal setting, where we're just running it how we're used to. But one way we can actually speed it up without changing the algorithm at all is to add a level of parallelization to it. And so that's what threading does. And by parallelization, I mean, let's try to do some amount of code at the same time. So if we just kind of take a step back and not worry about the programming too much, then if you were to try and speed up taking the average of something, let's just say a really big list of numbers, what you might do is say, well, okay, person 1 is in charge of the first half of the list, and this is an odd list, so it's going to be a little uneven. Person 2 is going to have to do slightly more work, but that's okay, and then person 2 gets that stuff, right? So we say, person 1, you go add those numbers, person 2, you go add those numbers. And this is kind of like an intuitive way to speed this up, is you just divvy up some amount of work to multiple people. Okay, so we can actually do that in programs as well. We can divvy up work to go to different, what we're calling threads here, that are going to execute code at the same time, or at least close to the same time concurrently, which means that they're both loaded at the same time at bare minimum. They both might run at the same time too, but we'll kind of leave that hanging, and just we'll assume that they're running at the same time, like executing as well. So is that clear so far? It's just like a common sense way that we could speed this up, is just give everybody a part of the array and have them add it up. And we don't have to just split this into two parts. We could split this into as many people as we have, right? We could give them all a certain amount of numbers and have them add it up. And that would generally go faster. So now let's get into how we do that. So what we have here is the idea of a thread. So as I said, this was person 1 and person 2. What we're going to do is we're going to create two threads. And thread 1 is going to look at the first half of the array. I'll just have it point up here, and then thread 2 is going to look at the second half of the array. And then if we consider after they're done adding, they're only really going to have a partial result of what we're looking for a average. So we need to actually get like the full sum of the whole thing. So after these guys are done, thread 1 gets its sum. We'll just say S1, and thread 2 gets its sum, S2, from adding the second part of it. What we need to do is we need to put these together and then divide it, right? Divide it by the size. So we got to consider what's going on here. These two run at the same time, just like concurrently, meaning at the same time, concurrently. And then afterwards, they have to do some sort of joining, put their work together that they've done, and use that to finish. And this should work out to the sum, right? This part here would be the first half of the sum if you were to write the full formula for an average, and then this would be the second part of it. Okay. So let's actually go into the code for this really quick. So that's at least our intuition behind it. In order to use threads in C++, you need the thread library. So I've gone ahead and included that. And then I have some other constants here that we'll get into later. But basically, we have an array of size 10. And what we're going to do is we're going to have one thread add the first part of the array, and then the other thread add the second part of the array, and then we're just going to put them together and take the average. And so this is just all error checking. Don't have to worry too much about that. So what I do here is I create an array of floats. In this case, it's going to be size 10. We initialize it, so I just picked, I didn't want to type out all the numbers, so I just picked having it be 0, 1, 2, 3, etc. That it adds up, plus we can check that it works that way. And then I have the two sums that we have. So I have the S1 and S2 as first sum and second sum, which are going to store the results of the first thread executing and then the second thread executing. And then we actually get to the threading part. So let's discuss how you kick off a thread. In order to kick off a thread, you declare it like you would any other object, or call its constructor, which we'll do it that way in a little bit here. So I create a thread variable called first thread, and the way that the constructor works is it takes any number of parameters or any number of arguments, which is a little weird, but it will hopefully make sense. And the first argument that it takes is going to be the function that it's going to call. So you can actually give it free-floating code, which is called a lambda. I'm not going to do it that way, partially because I don't remember the syntax in C++, and partially so we can just reuse code and not have separate instances. But I have a function here called addNumbers that takes the array that is going to be adding numbers from. It takes where to start, the lower bound. It takes where it's going to stop adding the numbers, like where its cutoff point is. And then it has a pointer to the results. And then I just put a thread number here so that we can know when each thread is executing and kind of have an idea, right? So that's generally what we have. You'll notice that it actually returns void, which might seem strange at first, but generally when you're doing threading, you actually want to return things via a pointer, just kind of like indirectly rather than do an actual return value. It's just a little bit strange how you end up doing return values in threading, so it's common, at least in C++, not to do it that way. So instead of returning an integer, I'm just going to have the result be stored via a pointer, which is going to be by value reference. And so all this does down here is it goes from the lower bounds, there's just one for loop, it goes from the lower bound to the upper bound, adds all the numbers in the array in that point, and stores it in the result by dereferencing it, and then we just initialize the result to 0 so that the variable gets set beforehand. And then I just have a print here that says the thread started and the thread ended. So if we go back to this, our constructor is going to take the function that it wants to execute, or the lambda, which is just a piece of code you want it to execute, and then all of the arguments to that function afterwards. So they're not actually part of the call. You can kind of consider this as a variable in the form of a function name. So you notice I just give the function name, but no like left paren, right paren after it, right? So when you call a function, you put the left paren, right paren, and then a parameter list after it to tell it, okay, call this function with those parameters. In this case, we are using it as a variable where it says, hey, this is where the function is, probably like an address, and go call it with these arguments instead. So a little bit of a distinction there. And so what we're saying is go call the addNumbers function with the array, start at position 0, end at the halfway point, and then store the result in this first sum variable, and then here I just put the number of the thread so that we can identify it later, which is 1. And then we do the same thing with the second thread. So it's going to operate on this array, it's going to start at the halfway point, and then it's going to end at the very end of the array, and it's going to store its result in second sum. Now when we want these threads to join back up and meet, then we do that with the join function in C++. Basically, this just makes it sit and wait until the thread is done and returns from the function it's executing. In this case, both the first thread and the second thread need to be done with their addition before we go ahead and finish doing this. So there's something to consider about concurrent programming is you actually have no idea when these threads are going to finish. You have no idea if they're going to finish at the same time, which is very, very, very unlikely. And you can't even be guaranteed that they're going to finish in the order that you kick them off, or anything dependent on the amount of work that they do, or anything like that. I mean, we could have a whole semester of discussion about that. I'm sure it's kind of complicated. There's a lot of stuff that affects that. But if we just kind of consider what happens if they weren't to finish at the same time, which is probably going to be the case. If I was to just go to our array here, and thread 1 finishes all of its adding, it adds 4, 6, 7, and 10, but thread 2 is still kind of running slow, and it does 12 plus 15, but it hasn't finished adding 19 to its result, then if I just go based off of one thread finishing their work and do it, it'd be kind of like the first guy going over to the second guy and being like, you know, hey, I'm done, and bothering them, and you know they don't get to finish their work. So we need both of them to finish before we synchronize and add up. Otherwise, we're going to have an incomplete sum. And so that's why we have two consecutive joins here. Is the first thread is going to finish its work, the second thread is going to finish its work, and once they're both done, we can continue on with our program. So there should be no code in between these joins. Otherwise, they're going to do stuff while the other is still executing, which we don't want here. That'd be kind of unsafe. And then lastly, we put together their two sums, and then we just print it and divide it. So let's go ahead and run it here. Considering there are 10 items, the sum should be, if you remember, we had that sum for like, sorry, I gotta switch to a different mouse. We had that formula for like sum of integers. So the sum of this, if it's the numbers 0 to 10, actually, sorry, 0 to 9 should be 9 times the number after it, which is 10 divided by 2. So 9 times 10 is 90 divided by 2 is 45, which is the sum we get. And then the average, if there's 10 things, would just be 45 divided by 10, right, which is 4.5. And so there we go. We see it finishes, and it runs concurrently, and we have these things that kind of do some sort of speed up. So we haven't improved on the algorithm at all. If we were to look at the time complexity, they do still have to go through every single number, which is kind of how we measure that, right? Like every number has to be counted, but they do it at the same time, which is where our speed up comes. And this is how a lot of speed up occurs in computers, at least in modern machines, is that we have these things run in parallel. We have them execute code at the exact same time, and that's how they get a fair amount of their speed up, right? This is kind of like the idea behind graphics cards, if you're familiar with those. Those just have a bunch of really simple operations that they just run all at the same time, and that's kind of how that gets a lot of speed up. Cool. One other thing to actually note about this, I probably should have thrown it in line. I guess I just didn't, or maybe there's an issue with the stream printing since these things are running at the same time. But you notice what I said earlier kind of applies here. Thread 1 starts, thread 2 starts immediately afterwards, and then thread 2 finishes before thread 1. Even though thread 1 was the first one to start, and they had an equal amount of work in this specific example with the code, thread 2 finished before thread 1. And again, there's a lot of factors that could affect that, but just something to keep in mind is that even if we run these things at the same time, there's no guarantee that they'll finish at the exact same moment. And in fact, they'll usually kind of finish randomly, and there's no way to predict it. But yeah, we get some speed up there. So what I do now is maybe generalize this so that we can do this for any number of threads and maybe do it on a bigger array. And then we could potentially time it. I guess I do have it in Visual Studio right now, which would be kind of inconvenient to time. But at least we'll try to get an idea of how we would do this for some number of threads. Now this code I have up here at the top is just for a command line argument that is going to set how many threads we want to execute. I think I have it as 6 right now. If we go to the properties, 5, I guess. So we have five different threads. Let's try to make this so that it is more generic. So I'm going to bump this array size up to 100. And then on top of that, let's remove this first and second thread and these sums and try to make it more general. I'm just going to comment these out for now. And so I want to change this to just kick off some number of threads and then keep track of them. Okay. So does anybody have a guess as to how we're going to do that? Can you think of a data structure that we commonly use when you want to store a bunch of things next to each other? An array, right? Yep. So let's just make an array of threads then. So let's make a thread array, and I'm going to do it as a thread pointer, I guess. A thread pointer array. I think this is the syntax for doing this statically. I've actually never really tried it this way, but hopefully this is right. We'll call this T array for thread array, and we'll make it as big as the amount of threads that we want to put in there. Count. Oh, that is, yeah, okay. I need to do this dynamically. Let's do it this way. So equals new, I'm going to do this as pointers. And the reason I'm doing that is just so it doesn't automatically create any threads. It just, it's a pointer, so it's not going to allocate anything. So we'll make an array for the threads. Let's also make an array for the results of the threads. This is all floats that they return, right, is their sum. So we'll make a float array. I need to make that a pointer again because we need to dynamically allocate it. So let's just call this the sum array. And we'll allocate it to be an array of floats corresponding to each thread. So they can each store it in there. And then that should be good. So we're going to need 2 loops. We're going to need 1 loop now to go through the array and kick off all the threads and store where they are. And then another loop to synchronize them all on. So let's start with this one. Equals 0, I less than thread count, I plus plus. So for as many threads as we want to create, let's go ahead and create them. We want them to call the add numbers function. And then I think it was lower bound, upper bound result. So the lower bound is going to be I, and then the upper bound will be I plus. I guess we should calculate this in advance. So let's figure out how much each thread needs to add as part of that array. So if we kind of consider they each get like an equal number of parts, right? So, well, not necessarily, but I'm going to do it in such a way that they kind of do. So int, what's it called? We'll just say sub array size, how much they get, is going to be equal to the amount of things that are in the array, which is the array size. I called it R size. And then we're dividing it into as many parts as there are threads, right? So we just need to split it up into thread many pieces. Okay, so this should be how much each thread executes. Now, there is an exception to this, which is if the array size is not evenly divisible by the thread count, then the last thread is going to get less work than the rest of them. Probably not by a whole lot, but if we kind of go back to our example here, person 1 was doing more work than person 2, or these threads, thread 1 was doing more work than thread 2. So the last thread is going to potentially have less work to do. And so what I want to do is address that fact. We could kind of divvy it up a little bit better if we try to work it out in a certain way. But I think what I'm going to do is I'm just going to kick off all the threads except for the last one. And then the last one I'm just going to have operate up to the end, essentially. So we could have a disparity in the amount of stuff that each of them are doing. I'm actually going to do thread count -1. And I guess this would have to be I times subarray size. And this would be I plus 1 times subarray size. And if you need me to justify any of these, please let me know. I'm just kind of writing them. So we have lower, upper, result, and then thread number. So result is going to be, we made an array for that, right? So sum array sub I, which I think is full of float pointers anyway, so this is probably okay. Oh no, it's not full of float pointers. I think I need to make an ampersand there, so I actually need to pass it by reference. I need to get the address of the thing in order to pass it correctly. And then the last part was the thread number, which is just I. I'm just going to say this is kick off the first n-1 threads. And then I'm just, for safety's sake, I'm going to kick off the last thread separately because it might get an uneven amount of work to do. Right, so we'll say tr sub thread count -1 is equal to a new thread. I've done it in such a way that the I is going to be left over from the for loop, so it should still be I times subarray size, and then we just want it to go to the end of the array, so I'm going to say to r size, and then we need to give it the part of the array that it needs to operate on, where it needs to store its results, so sum r sub the last thing in the array, which is thread count -1, and then this thread is going to be thread count -1. Okay, so basically we're just saying that the last one is going to get the potentially unequal amount. We just want it to go from wherever the last thread we kicked off ended to the very end of the array, since that might not be a consistent amount. Okay, so I think that handles kicking them off, and then we want to synchronize them like we did last time. We just want all the threads to sit and wait until all the threads are done. Even though we could kind of parallelize some of it, I'm sure, we're just going to go for a simple part here, which is we're going to go for thread counts. Now, there's nothing special about synchronizing them, so I don't need to do any extra cases. We'll just go through the array, and we will sit and wait until each thread has finished executing. So essentially, we'll wait for thread 1 to finish, and then we'll next wait for thread 2 to finish, and we'll just check in with them one at a time until each of them finishes in order. So we have that now, and then we lastly need to go through and calculate the average, which will be pretty easy. It's basically just taking the average again, if you kind of consider what we're doing here. We went through and added them all up, and then we were going to divide. And we actually just need to do that again, basically, just with all of the subarrays that we've got. So we just need to go through each part that each thread has finished adding together and add all those together. ILS thread count again, I++, and then the full sum plus equals the sum array that we had, sub I. So this should now hopefully kick off some more threads that we can control and add them up. And I do seem to get an error. Invoke no matching overloaded function found on line 43, which I assume is our... Oh, it's of the thread. I think it's yelling at me for what I have here. I mean, I think this should be right. Oh, I also need to initialize this to 0. That was my bad. Why is it getting mad at me? Am I calling these with the wrong number of arguments, or did I make a typo? I think that's still outdated. No. Did I make a typo somewhere? Maybe it doesn't want me to pass this by reference. I think that's going to be a type error, though. No. If somebody sees a typo, let me know. I don't see anything. Oh, never mind. I do see one. I forgot to put the function that we're calling on the first part there. I forgot to tell it what we're calling. I think I do need. Whoops. I need to add back that ampersand. No. It's still getting mad at me. Expects one argument's 5 provided. 1, 2, 3, 4. All right, maybe we'll do it this way. Maybe it doesn't like the fact that I have thread pointers. No. It doesn't help that they don't give you very helpful messages on these. No expects one argument. Out of curiosity, let me just comment all this out and see if it is at least okay with what I have. Oh, I mean, it's got to be okay with this, right? So it's just going to print 0. Yeah. Is it the thread kicking off? I think it doesn't like the way I'm kicking off the threads. That's definitely the case. If I had to guess, maybe I just made a typo and there's a mistake with the arguments, but I don't really see where that is. So it's an array, lower, upper result. Oh, I wonder if this because it's not a static. No, it is a static array. Oh, duh. I didn't actually put the array. We had an array that we are adding from, right? And I totally spaced it. It was called R. I made a typo and I wasn't calling it right. Unfortunately, with threads, it's not going to give you a helpful compiler message like you would normally see where it says, you know, this type mismatches or whatever, or you have an incorrect amount of things. Hopefully it's okay with it now. Okay, there we go. May have had, oh no, I accidentally clicked the breakpoint. And now if it runs, we see that I have the sum commented out, so it doesn't give us any sort of meaningful answer. Okay. Uncomment that. Run it again. Then threads finished. I don't even think we got any messages about threads starting. I guess we did. Yeah, there they are. They'll start and finish. We get a sum of 4950, which I think sounds right. Should be about 99 times 100 divided by 2, which I think that sounds fair because 90 times 5 would be not that. And an average of 49.5. 990 times, 990 times 5 would be 450 plus 45, which is 495. With the 0 at the end. Yeah. All right. So that is right. So we do get the right answer, and we do see that all the threads kicked off right. So we got kind of just jarbled mess in terms of the output because they're all trying to write to the screen at the same time and then kind of step on each other's feet. But we see that they all finish, and again we see seemingly that one finishes way after everybody else, which might seem counterintuitive at first, but just that's how it goes sometimes. Okay, but there we go. We have a way to generically make as many threads as we want and have them solve our problem and kick it off. So any questions so far on that? I know we stumbled there for a little bit, or I stumbled there for a little bit. Is it all making sense, at least what's happening with our code and why we use an array? Yeah, okay, fair enough. And if anybody has questions, just stop me. Okay, so that's just generally how we kick off threads, and we can use those to do problems in parallel. Now then there comes the question of what kind of problems are we able to parallelize, and are we able to parallelize the whole problem? I want to go back first to this example that we've been doing where we've been adding up all the numbers in an array and having the threads add up their own individual parts. Now the majority of this is parallelizable, but if you notice, not all of it is. So even in this example where we have two threads, we have them both calculate their own sums and find the specific sum of the part of the array. But at some point, they have to stop and join up together and put their results together, right? And so no matter how hard we try, and we could certainly do it a little bit with more and more threads, this can never really run concurrently. Right? So once they're done, they have to stop running independently of one another and figure out the result on one single thread, i.e. just the original program that was running. Right? So something to consider about parallelizing problems is that not all of it is going to necessarily be able to be done at the same time, and that at some point you're probably going to have to join them and have one master thread finish the work for everybody else. And that's what we see here, although it is pretty minor, right? It's just adding the final results and putting them together there. So there's two more things I wanted to talk about just to be aware of when doing threads, which is memory usage, and then also knowing to use threads, I guess, in a smart way and not try to solve problems by just throwing a bunch of threads at them. You'll actually, maybe if you look at this, see a way in which if I threw too many threads at this, it actually probably runs slower. Can somebody think of an example? If I was to throw more threads at this, can you think of something that might be an issue? Or where I might experience slowdown? Which seems counterintuitive, right? But can you think of anything that might be bad for threading? Right, you got it. Yeah, having a thread for each number. Right, so in this case, I have 7 things in the array. If I made 7 threads, it's actually going to run slower than if you just didn't have it run in parallel, because you are taking all the time to create all those threads, telling them to go kick off, which it has to do with the operating system. Usually you have to ask it for a thread. And if I asked one person to add that number and then another thread to add that one and this one and that one and that one and that one, then each of them are going to do no work whatsoever. They're just going to look at the number and be like, great, here it is, and return it. And so we kind of end up running it a lot slower, right? And generally you're going to notice the same thing. Even if I was to kick it off with, let's just say, 5 threads, then some of them are actually still going to get 1 in this case, right? And it's going to be kind of slow. So in cases where each thread is going to get very, very little work, not enough work that it's going to offset the expense of starting a thread in the first place, because there is time that needs to be done to start it, then that's going to be a case in which threading is a bad idea. So as nice as it seems to just throw threads at a problem and say, hey, split this up into 100 pieces, if you do it and aren't aware of how your problem works or the size of your problem, then that's not a smart way of using threads. So good job, you caught that. That's very good. Right, so I think that handles the main case of where threads are going to be slowing our program down. The other thing I wanted to mention is that you need to be very, very careful about the way that you use threads when interacting with the same memory space. So we don't have much of an issue in this specific algorithm, because the way we're doing it is we're saying, hey, first thread go do this part of the array, second thread go do this part of the array, and all they do is they read that number and then add it to that running sum that they keep, right? And so they don't step on each other's feet at all, and it would, we're trying to avoid that anyways. If they added the same number twice, then we'd have an issue. But one scenario that we could come up with, which maybe is just a beginner mistake on this, would be, well, okay, maybe I want to try to speed this up a little bit. So I do thread 1, let that finish with whatever it's doing. Actually, I guess this would still work, but I wouldn't do it this way. Well, yeah, actually, sorry, I'm going to do it this way. So let's say we join them down here, but before we join them, we try to take the full sum. We'll just say plus equals the first part, the first sum. And then let me move this down a little bit. Oh, great, it works like that. And then let's say we add the second number to it. So we make the assumption that the first thread is going to finish before the second thread, and we try to add its sum into the full sum before the second sum gets there. Now, we've kind of seen with that execution that we don't know when they're going to finish. So first off, one of the issues here is the order in which we wrote this. We don't know that the first thread is going to finish before the second thread. So, the first sum might not be complete when it does the first write here, and the second sum might be done. So maybe we get some sort of incomplete thing, or vice versa, where we also get an incomplete scenario. But there's also another problem, which is actually if they finish at the same time. So actually, if these finish at the same time and both try to add to the full sum at the exact same moment, we might actually have an issue. We haven't talked a whole lot about hardware aside from just taking a glance at memory. But there's basically two operations that can happen. There's a read and there's a write, which we've seen with like getting and setting. So you can either have something on the left-hand side of an equal sign, which means the thing is getting written to, it's getting assigned the value, or you can have something on the right-hand side of an equal sign, which means it's getting read from. And I guess the same thing goes for any sort of operation like plus or minus. There's no write to a variable, it reads the value of it and does the operation. And so what we might have here is, my pen being super finicky, is if we have the full sum in memory, and this is its location, it occupies the space, if the first thread goes and tries to put the first sum in there, and the second sum goes and tries to put it in there, and they both try to do plus equal at the same time. So let's say the first sum is like 10 and the second sum is 12. What will actually happen is this will go, and let's just say thread 1 gets there first. It will write 10 to that location, and then if the 12 gets there before this line doesn't sort of like registering to get there at exactly the same moment, it's actually just going to overwrite this and put the 12 rather than do the plus equal operation, because it has some outdated notion of what full sum is, and they're going to just step on each other's feet and one's going to overwrite the other. I'm doing this kind of just, from a step back. It's not fully, I'm not explaining it in full detail, I guess. We have to have some knowledge of hardware, so I'll leave other classes to talk about that. But if we have this thing where they're both trying to access a resource at the same time, usually memory, then this is what's called a race condition. They've raced each other, and they didn't wait for each other, and they've stepped on each other's feet, and now we have this big issue. And so this is why we have to do this synchronization that we have had earlier, where we wait for all the threads to join before we do some sort of sum. If you're using the same memory space with multiple threads, there's a chance they're going to just overthrow each other or step on each other's feet and throw out their values, and even potentially use values that they shouldn't be using that are outdated. So there's a notion of locking these things that I won't mention just or won't explain in detail, but you can use like booleans to say, hey, this person is writing and this person is not writing. And there's algorithms for checking that. It's usually taught in the operating systems course 370. I'm not going to go into full detail, and I don't think I remember a whole lot of them outside of Spinlock off the top of my head anyways. But yeah, just something to be aware of. Don't use the same memory space with variables, especially if you're writing. If you're reading, then that's fine. We don't have that problem here because these things are looking at separate parts of the array, but try not to make them overlap at all because that's going to cause a lot of issues. Okay, so there's certain algorithms that you should try not to do with parallelization. All right, so last thing I want to talk about, hopefully we'll have time to finish it, is I want to talk about an algorithm that you should use parallelization for, or that you can use parallelization for something really common, which is sorting. So an example of something that's not easily parallelizable would be bubble sort. So if we kind of consider that always like runs through the array, you have some array, and it runs through from start to finish and bubbles up numbers. I can't really parallelize that very well because if I split it into parts, then it's only going to really split, or it's only going to sort part of it, right? And then we still have to sort the whole array. And it's like somewhat sorted, and we can maybe optimize it a little bit, but bubble sort's not great for parallelization because just because of the way it works, right? It starts at the end, or starts at the beginning and goes to the end, and goes through it every single time. And if we block it off and tell it it's only allowed to have this specific part of the array, then it can't go from the beginning to the end, so it's not really doing a great job of what it does. Right, so bubble sort is bad in general, but it is bad for parallelization. And if we try to do it in a way where we maybe just have like one go through the array and we don't block it off, and then we have another pointer follow it and try to update it as it like follows along, we again have some race conditions where we can't be guaranteed that they're going at the same rate. So that's another issue we would have with bubble sort. So there's no good way to parallelize bubble sort really that makes it super efficient. We need some sort of other algorithm. We had a little bit of intuition there. I just erased it, but you know, a common sense way again to do some sort of divvying up problems is to just split it to equal parts and let each thread get that specific part. So just simple divide and conquer, you know, split it up evenly and let everybody do what they would do on the whole array, just in a specific spot, and then figure out what to do later once they're done with their work. So I want to propose an algorithm that is pretty good for that, and that you can do with a uniprocessor system with just one thread, you know, not with all these things operating separately. But it is pretty good for parallelization, and that specific sorting algorithm is called merge sort. Let's go to a new slide. So the way merge sort works, at least from just a zoomed out kind of perspective, is it just splits things into parts and lets them work things out. So let's just say I have this array here. The way merge sort works is it splits the array into two equal parts and lets each of those parts get sorted independently. The way merge sort works is it says, okay, here's the cutoff point, it's halfway. Let's sort the thing to the left and then sort the thing to the right. And so you can see why this is good for parallelization. It's already pretty easy to split things up if you're just, you know, saying sort the thing to the left and sort the thing to the right. Now, we kind of have a problem here because if I just generically say, well, go sort this thing, then you know, how do I do it? Do I just do bubble sort on this left side and then do bubble sort on the right side? Then we're just kind of back to the issue we had earlier where we're really just splitting it up and doing bubble sort again. And so merge sort is an algorithm that is best done recursively, I would say. And so what it does is every time you give it a new array, you split it into two subsequent arrays, one being the left half and one being the right half, and you sort each of those halves. So this one splits into an array of size 4 and a size 3, and it goes and recursively sorts each of those. So this is going to receive an array of size 4, and it's going to say, okay, I'm going to split that into 2 more pieces, one being the left-hand side, split it here, and then one being right-hand side, and this will do the same thing. And then as we do with recursion, we continue to go through this and recursively say, okay, sort the left, sort the right, over and over again, until we reach some sort of base case. Something that's trivial to solve, something that's really easy and you can write in maybe a few lines. And the cutoff point I'm going to do for the sake of our merge sort is I'm just going to say if we get an array that's of either size 2 or of size 1, I'm going to say that's trivial to sort, because that's pretty obvious how to sort an array of 2 things and an array of 1 thing. If you're sorting an array of 1 thing, well, you're done. That's great, because if it's 1 thing, then there's nothing to sort. And if it's an array of 2 things, then all you have to do is compare those 2 things, and then if they're out of order, then you swap them. If not, then that's great. So for merge sort here, I'm going to say if the array size equals 2 or it equals 1, then we'd probably split these up, actually. I would probably do 2 different ifs, but sort the trivial stuff, do those pretty easily, and then we're done. So you can see here, we can use the idea of recursion for things like sorting. And this is actually significantly faster than bubble sort, but it does have a drawback, which we'll see as we go here. So let's say I have my array 1, 4, 3, 2, 8, 7, 0. Let's say 7, 0, 8, 7, 0, 1, 4, 3, and 2, 1, 4, 3, and 2. So what we do is we sort each of these in their kind of like atomic structure, their trivial cases. So this one's great, this one's already done. This one we just swap the 2, so 2 comes before 3. This one's a size 1, so there's nothing to do, and then 0 comes before 7, right? Now, we have an issue when we try to go back up this tree. So after we've told it to sort the left and the right-hand side, we might have an issue. So if I was to just put these back together, and I let these only work on its own. So let's say I go back to trying to put these arrays back together so that they equal one big array again. Hence, merging them, named merge sort. Then if I put these back together where they just sorted the parts that they were given, then this would sort 1 and 4 because it saw just the numbers 1 and 4 and put those in the right order, and then 2 and 3 and it would put those in the right order. But now this subarray is not sorted correctly, right? And so we're either going to have to run another sorting algorithm on this, which again defeats the whole purpose of doing a separate sorting algorithm, or we're going to need to be smarter about this. So let's try to be smarter about this. So rather than just mash them straight together and merge them straight up, what we're going to want to do is kind of look at each array and sort them as we put them back together. So as we merge them, we're going to look through. And so we can kind of shortcut this. What I'm going to do is I'm going to keep 2 pointers, 1 to the first array and 1 to the second array, and I'm going to let them compare to each other what's going on and insert as needed. So actually I'm going to keep a third pointer as well. Probably use 3 colors. I already have a whole lot of colors going on already. I'll use orange there. So we're going to keep a pointer to each of these. And we're going to look at how they relate to each other and then put them into the array in the correct order. So if we, considering the fact that they're sorted already, I guess I should probably move this pointer down to this case. So it's pointing at the 2. What we want to do is we want to merge the number 1 and the number 2 into our array. So what we're going to do is we're going to take the lesser of these and merge based off that one. So if I'm looking at 1 and 2, I'm going to do 1, and then I'm going to move the pointer past the 1 since now I've inserted into the correct array. So we're just going to slowly go through each element that all of these have and put them in the right place. Then if we look at the left array, the next element in the left array is 4, and the next element in this array is 2, smaller of which is 2. So we add the 2 and then make the pointer of our second array go up. And then the last two numbers we have left are 3 and 4. 3 is smaller between those two, so we say 3 is done. And now we're at the end of this array, so there's nothing left. Once you run out of stuff in one array, you can just put the rest of the stuff from the other array, which is just 4 here. Does that make sense? How this merging process works is you keep, I wasn't updating this pointer properly, but we're pointing to where we're putting it in the array, is you look at from the beginning, both of them, and then whichever one's smaller, you just put it in its final position in our merged array. Yeah, okay, fair enough. And I'm not going to write the code because I don't think we'll have time to do it, but feel free to look it up on our website. It's a very common algorithm, so I'm sure you'll find a code for it if you're curious. So I'm just going to move a little bit forward. I'm going to merge these two, so this will obviously be 0, 7, 8, right? It'll keep a pointer to this one. We'll add 0 first, then the 7, then the 8. We've merged these two together, and then we'll need to merge these ones together. So if we just quickly do it, then the way this will work is we'll look at the first two of these ones, 0 is smaller, then we'll look at the smallest between 1 and 7, which is 1. We'll look at the smallest between 2 and 7, which is 2. We'll look at the smallest between 3 and 7, which is 3. We'll look at the smallest between 4 and 7, which is 4. And then there's nothing left in this array anymore. It's already added everything, so we just append whatever's in the other array to it, and it's done. So we just finish to do the 7 and 8. So hopefully, even though I rushed through that, that makes sense. And we get a sorted array. Once we're finally done merging everything that we kicked off, we get back to our thing here. Right, so just to mention, this algorithm is O of n log n, which I don't think I'll have time to prove, but you can just take my word for it that that is what we have in this case. The n comes from the fact that there are n elements in the array, and the log n comes from how many times we're able to break it down. Again, if you consider logarithms are the inverse function of exponentiation, so whereas we're not doubling the array, we're cutting it into halves every single time, then that's where the logarithm comes from. It's the opposite of doubling. Right, so we have a new algorithm. It's generally better than bubble sort in terms of its runtime. I did say it had a catch to it, which is specifically that during this merging process, we have to create a new array to merge things into, right? Because we kind of have an issue of needing to keep like two separate pointers to the arrays that we're merging, which means that it consumes more memory than just the standard bubble sort, because we're not just holding one array, we're probably holding a couple copies of it, if anything, which is not great, but I mean, it's probably worth the time trade-off. But what we're concerned with, because we've been talking about threads this class, is how we can apply threads to this. Okay, so if we consider what's going on here, we can kick off two threads immediately every single time we do this. So every time we are going to split this array up into two parts, we can have a different thread work on each part. So I'm just going to kind of quickly, I don't know what color I want to use. Let's just say, let's use purple. I'm going to number where we would put each thread. So we would probably put one thread up here that handles the merging of the final thing. We would kick off a thread to work on this one, a thread to work on this one, a thread to sort just these two numbers, a thread to sort these two numbers, a thread that does nothing essentially, just gets the number and returns it, and then another thread to sort those two numbers. And then as we merge them, this is going to be the thread 2 we saw up here. It's going to, after it asks these two threads to go and sort their parts, it's going to receive their parts and merge them together. So thread 2 does this work as well. Thread 3 does this work as well. And thread 1 is going to do the final merging. So again, we can't run it all in parallelization. We have to do some waiting and then merge the parts when they're done. Again, kind of like the adding of numbers that we had earlier for like taking an average. We do have to do some weighting, and we can't have it just work on as many parts as possible. But we can at least have it do some of the work at the same time. And the fact that it does work in an uneven amount of time is, I guess, both a good thing and a bad thing. So if the threads 2, 4, and 5 are just exceptionally fast, then they might actually finish all of this stuff and then get stuck waiting on thread 3 to finish its parts. At any given point, you might be stuck waiting for another thread to finish, which is kind of one of the drawbacks, I guess, which is kind of unavoidable. Just some threads are going to be slow. So this program only runs as fast as its slowest thread. That's one way to think about it. So there's some sort of weakest link. Okay, so I think that's just kind of an overview of this here. We do still have quite a bit of time left. I don't know, did you guys want to try to program this? I can definitely try to write it with parallelization. Maybe just to start. Yeah, fair enough. We'll see how far we get. I'll try to do this merge sort. And one other thing I wanted to mention was just, I hope this demonstrates how useful recursion is. We kind of just get a base look at it in this class, but you can use it to do some really cool things. Right, so I'm going to do a void merge sort, and it's going to take an array. I'm just going to do integers this time. Array. We'll say the size of that array. Is that going to be sufficient? Probably. I think that's okay. And I think that's all right. I think that's all we really need. I'll fix it if I made a mistake, but I think that's probably fine. Okay, so let's go down here and try to write this. Okay, so we want to do this recursively. Then first things first, let's just do our base case. So if the size is 0, then that's easy, just return. No big deal there. And if the size is equal to 1, oh, I'm sorry, if size is equal to 1 and if size is equal to 2. So if size is equal to 1, then that's trivial. We just don't need to do anything at all. And if the size is 2, then all we need to do is compare the things that are right next to each other and put them in the right order. So we'll say if R0 is greater than R1, that's really the only case we need to consider, is that they're out of order. Then we will create a temporary variable equals R0. R0 equals R1, and R1 equals temp. Temp. So if there are 2 things, just check if they're out of order and swap if needed. And then we can return immediately after that because we have no more work to do. That's done. And then we have to do the recursive part. So with threading, this is going to be a little more difficult, but that's okay. What we're going to want to do is we're going to want 2 threads for each half the array. And I think what I'm going to do is I'm going to copy over into 2 separate arrays. So I'm going to do an int pointer left array, which is going to equal a new integer array of size divided by 2, so give it half. And then I'm going to do an integer pointer right array equals new int size minus size divided by 2. Again, I'm doing it in a bit of a strange way. You know, you would think I would just do size divided by 2, size divided by 2, but I'm doing this so that it, if it's unequal sizes, then we don't have to worry too much about that. I'm sure, again, there's probably a better way that I could do this with like modulo, but I'm just gonna actually, if it's that, yeah, I could do this better. This will be minus size mod 2. That's not that much better, but I think this is probably fine. Okay. So now we have two arrays, the left array and the right array, and I'm just going to copy over. So allocate the left array and right array, and then copy over. And the reason we're copying over is just for the sake of making the merge easier so that we can keep the pointers separate. I'm going to do one thing here, so let's just make it in int I equals 0. I know I could do this with the threads as well, but I'm just going to be lazy about this. I guess I don't really need the equals 0 part. I equals 0, I less than size divided by 2. For the sake of making this easier, let's just say the left size is equal to this, and the right size is that, so I don't have to keep recalculating these because I realize I'm going to have to use these numbers a bunch. Calculate how big each one is. So for I equals 0, I less than left size, I plus plus. We're going to go into our left array and copy over left array sub I equals array sub I. And then we need to copy the right array over. So I equals 0, I less than right size, I plus plus. And then right array sub I will be equal to r sub left size plus I. I don't think that goes out of bounds. Should be okay. So we'll have the left array copy over everything up to a certain point, and then the right array picks up where it left off at that left size index, and then counts after it until it's done reading all the stuff it needs to do. Okay, so we've divvied this up into two arrays. Now we need to go and do our recursive call where we ask two threads to recursively do this. So I'm just going to do two threads, no array, because we know there's going to be two. It's not variable or anything. So we'll say this is the left thread. And we want this to recursively call this function, which is called merge sort, and takes the array and the size. So merge sort, and we're going to call it with the array that it's sorting, which is going to sort the left array, and it's going to be of size left size. And then the right thread is going to be pretty similar. It's going to operate on the right array that we're going to give it, do merge sort on it, and it's going to have a size of the right array. Sort each side. And then lastly, we just need to do the actual merging. So merge the two arrays together. Okay, so I'm going to do a thing called left index equals 0, right index equals 0, and then merge index equals 0. Basically just keep track of three, I say pointers, but I don't really mean pointer, I mean like indices into the array that are going to help us with the left, the right, and the middle. Okay, So we'll say while left index is less than left size, while we still have things that we need to merge from the left array, and we'll do the same thing for the right array. So while the right index is less than the right size, and I think that's fine. We'll just do that. Then what we need to do is check which one of the two that we need to put into the array. So what we'll say is if the left array sub left index is less than the right array sub right index, then this tells us that the thing in the left array is smaller than the thing in the right array, which means that the object we need to put into our merged array is going to be, so merge index sub, or sorry, array submerge index, which I think we just called R. So R sub merge index is equal to the left one. So if the left one is the smaller of the two, we put the left one into our merged array, then we increment the merge index and we increment the left index, since we've consumed one from the left array and we've also put a thing into the merge, so we need to increment both of those. And then else we know that we need to go grab something out of the right array instead, which means we're going to go and put into our array at the merge index again from the right array instead of the left array, and use the index we are using to address that. And then again, merge index plus plus and right index plus plus. I have a typo. Oh, I forgot to put something cool. There we go. Right, so this is going to go through at each individual point, is going to check, is the left one smaller? If so, it's going to put the left one in our merged array. If the right one's smaller, it's going to put the right one in the merged array. And then afterwards, what we need to do is we need to check which one has the remaining things left over that we just need to put into the array. So I'm going to say if left index is less than left size, then the left array has leftovers. Basically, if it hasn't reached the end yet, then we need to finish copying over all the stuff. And we know from earlier that our while loop only breaks if one of them has reached the end of their array and has finished like putting all of its stuff in the merged array. In that case, we will go from while left index. Well, actually, yeah. I just do this with a while loop. While left index is less than left size, then we will go into our array, put it wherever the next thing is in the array that we need to put is, retrieve it from the left array, and get it from the left index. In fact, I think this is just the same code that we had up here, so I'm just going to copy and paste it. And then I'm going to have the same thing for the right side. Basically, if it's not done getting all the things from the right array, then we know that the left array was the one that is out of stuff. It's leftovers, and we just need to grab all the stuff from the right array and put it at the end. Right index. Right size. All right, and I think that's done with the merging part, and it would just return after that, so we would be done. Okay, so we both have a faster algorithm now, and we're able to parallelize it by kicking off these threads really quick. I know we're at the end of class, but let's just really quick try to make a second array. Let's go down here and do some sorting. So we'll just say sort. We'll do an integer array. We'll make it the array size. for I equals 0, I less than array size equals plus, and then, I don't know, let's just sort it. R sub I equals 300 minus I. We'll just make it go in descending order so that it actually has some sorting to do. And then I'm going to print out the array. Just quickly, not formatted or anything, be fine. And then we just need to kick off the original thread. So thread sort thread, and that's going to call merge sort. It's going to do it with the array that we wanted to sort, and it's going to be of size array size. Okay, and then we'll wait for it to finish. So hopefully this works. We'll just check really quick. If it doesn't, I'll fix it before I put it on canvas. Okay. Oh no, I got an error, I think. Potentially just did too many threads. I'm not too sure. It didn't tell me anything. It just made a mean noise. So I'm going to assume something happened. I guess I'll try to fix it later. But hopefully you at least get the idea of where threads are helpful now and why recursion can be helpful with these things, and at least have an idea of how to start using threads in your programming. So I'll let you think about it. You can use it for tons of different applications. It doesn't just have to be simple stuff like sorting and adding. You can use it for a lot of speed up. So I guess on that note, we don't have class on Thursday, so I hope everybody has a good weekend. And then next week will be study week. If you have any questions on exam material or anything you want to cover in particular, just feel free to bring it to class and ask about it, and we'll try to cover it. So I guess I will see you guys next week, and have a good weekend.